before class assignment number 5, I want you to write a spreadsheet to complete the stress calculations that you've done in a previous problem. I want you to do a spreadsheet that will allow the user to change any of the parameters and have the resulting stress update correctly. And I also want you to use conditional formatting so that the principal stresses and maximum in-plane shear stress will be highlighted red if they are above an allowable level and green if they are in the safe zone. So let's do this one step at a time. Part 1, I want you to set up a spreadsheet the way I have shown. Notice I have some groups of variables, dimensions, external loads, stresses, etc. And the first column that I have here is the description of the variable. And then I leave a place for the value of that variable and a column for the units of the variable. Let me show you how I do these groupings. For instance, let's do external loads. See, the text is oriented vertically. What I do is I type in the text, external loads, into a cell, and I take those cells and merge and center them, and then I will do an alignment, and I will change the alignment to be vertical. I'll also select to wrap the text. That way, if the text is too big, it will automatically go down to the second line. So that's how I've done these cells here. I also want to show you how I'm doing the Greek letters with the subscripts. I'll do an insert a symbol, insert a Greek symbol, and now I have all my Greek letters that I have access to. Let's insert sigma, and I'm going to put a 1 there, and let's make it a subscript. Go to font, subscript. Now I have my Greek letter with a subscript. And I also want you to fill in this column the ID of each pipe. This mini table shows the nominal pipe sizes, the OD, and the wall thickness of the pipe. Let's also compute the ID of the pipe, inner diameter. Inner diameter is the outer diameter, subtract out 2 times the wall thickness. And now we'll copy that formula down, and now we have a complete table that shows the pipe sizes for these standard pipes. Go ahead and pause the video and complete this part of the assignment. Okay, part 2. I want you to fill in these cells in the dimensions group. Of course, dimension 1 was 12 inches, dimension 2 is 8 inches. Now for pipe size, I want you to be able to select from a drop-down list one of these standard pipe sizes from the table. I'll show you how that's done. If you go to the Data tab, into Data Validation, right now by default that cell will accept any value. Let's only allow it to accept values from a list. And here's the source of the list. So now it shows for this cell a little drop-down arrow. So now I can drop that down and I could choose from the list. In this case, I'm going to choose 1/2 inch. Now for the OD, I want it to go to this table and look up the OD. So I'm not going to type in an OD here. I want it to look up in the table the OD. I'm going to use a built-in function called value lookup, VLOOKUP. That VLOOKUP requires a value. We'll look for that value in this table, and it will return column number 2. And I want to make sure that it's an exact match. So it goes to the table and finds 1/2 inch pipe, returns the value in column 2. So now if I come here and I change and say 1 1/4 inch, it will automatically go and find that value. Let's do the same thing for the ID. VLOOKUP, that value in this table, return column 4, and I want an exact match. Now I'll go ahead and allow you to do these on your own. Go ahead and pause the video and compute the moment of inertia and the polar moment of inertia for part number 2. Okay, let's do it together. If you remember, moment of inertia for a round object is 1/4 pi r to the 4th. And since it's a pipe, I'm going to subtract the inner from the outer. So I'll go 1/4 times pi, and notice how I'm doing pi, times the diameter over 2, which is the radius, to the 4th. And I'm subtracting out the inner radius to the 4th, excuse me. And that gives me the moment of inertia. Polar moment of inertia, if you remember, total of the moment of inertia about the x and the y. And since the moment of inertia about x and y axis is the same in a circle, then it's just double the moment of inertia. Okay, go ahead and check your numbers. If you got them right, give yourself 1 point for part 2. Part 3, I want you to compute these 3 cells. Of course, this applied load is 100 pounds. Go ahead and pause the video and complete these other cells for part 3. Okay, let's do it together. The bending moment is the applied load multiplied by this distance, and the torsional moment is the applied load multiplied by this distance. Check your numbers and go ahead and give yourself 1 point if you got those correct. Part 4, I want you to complete these 2 cells. Determine the normal stress and shear stress at element A. Pause the video and work that out. Okay, let's do it together. The normal stress is caused by bending, which is equal to mc, which is divided by moment of inertia. Shear stress is Tc over J. Tc over J. Go ahead and compare your numbers and give yourself a point if you got that right. Okay. For part number 5, I want you to find the center of Moore's circle and the radius of Moore's circle. Go ahead and pause the video and work that out on your own. Okay, let's do it together. The center of Moore's circle is simply, that's the average, so let's take it over 2. And the radius of Moore's circle would be the square root of sum of the squares of the 2 sides of the triangle. It would be this number squared plus this number squared. Okay, check your numbers and give yourself 1 point if you got that right. Part 6, I want you to compute the principal stresses on that element and figure out the rotation angle for Moore's circle and the element. Go ahead and pause the video and complete this part. Okay, the principal stresses are the maximum normal stress that the element would encounter at any rotation. So if you look at Moore's circle, if we take the center of Moore's circle and add the radius, that gives us one of the principal stresses. If you take center of the circle and subtract the radius, it gives you the other principal stress. And for Moore's circle, we want to take the inverse tangent of the tau stress divided by this number. Now you'll notice that this actually comes up with an angle in radians. So what I would want to do here is I would want to convert that to degrees. I'll use the degrees function and convert the angle that comes out of that computation into degrees. So it's 33.7 degrees. And then if you remember, the element rotation is half of the Moore's circle rotation. Go ahead and compare those numbers and give yourself 1 point. Okay, now let's do part 7. I want you to compute the maximum in-plane shear stress and the rotation of Moore's circle in the element. Go ahead and pause the video and complete part 7. Okay, let's do it together. The maximum in-plane shear stress is equal to the radius of the circle. If you look at more circle, that becomes obvious. And the more circle rotation is 90 degrees, subtract the rotation to get to the principal stress. And the element rotation is half of the more circle rotation. Go ahead and compare your numbers to these and give yourself 1 point for part 7 if you got it right. Part 8, I want you to complete these cells. Let's assume we're using A36 steel, which has a yield strength of 36,000 psi, and let's assume a factor of safety of 2. Now go ahead and pause the video and complete these 2 cells. Okay, let's do it together. The allowable normal stress is the yield stress divided by the factor of safety. And the allowable shear stress is only 1/2 of the allowable normal stress. Metals are only half as strong in shear as they are in tension. So go ahead and check your numbers, and if you got that right, give yourself 1 point. Okay, for part 9, we're going to format this in a very professional way. First of all, let's format the borders. We'll put a thin border in between all the rows, and we'll surround it with a nice thick border. We'll do the same here for the heading. We'll do a thin border surrounded by a good, nice, thick border. And we'll do the same here for pipe sizes. We'll do a thin border surrounded by a nice, thick border. And let's also do the header surrounded by a nice, thick border. Alright, let's also take any parameters that the user would be able to change and highlight them yellow. Those the user would change, and the load would be able to be changed by the user, as well as the material properties and the factor of safety. So let's go and highlight those cells yellow. Now for the principal stresses as well as the maximum shear stress, we want to draw the user's attention to the results there. And we want to either have that red or green based on whether it's higher than or lower than an allowable limit. So what we'll do is we're just going to assume it's in the danger zone and color it red. Now for these normal stresses, I'm going to come here and do a conditional formatting and say it's red by default, but if those cells are less than the allowable stress, then let's format that and fill it green. And we'll also do it to this one here. We'll do this conditional formatting. If that cell is less than the allowable shear stress, we will highlight that green as well. In other words, if it's in the safe zone, we're going to go ahead and highlight it green. Otherwise, we'll let it be red in the danger zone. So go ahead and pause the video and complete that formatting, and make sure you do the conditional formatting here for those cells. Okay, for part 10, I want you to change the numbers in this cell and see if your stresses update correctly. Let's change distance 1 to 24 inches, distance 2 to 16 inches. And instead of a 1/2 inch pipe, let's choose a 2-inch pipe. And let's put a 300-pound load on it. And now I want you to check your numbers. The sigma 1 should be 14,139, and it should be green in the safe zone. Sigma 2, 1296, green in the safe zone. And tau max, 7718, green in the safe zone. If you got those right, give yourself 1 point for part 10. And we'll see you in class.